Okay. Good morning. Can you hear me?
Yes. Yes.
Perfect. Perfect. Okay. Very nice. So, yeah, I'll just take maybe at most 30 minutes or so to finish a few topics. So first, pertaining to some of the questions that were asked yesterday, I wanted to briefly mention a couple of complementary approaches for completeness to superfluidity, because this will shed light a little bit on what was discussed yesterday. So if you go back to our toy example of the complex scalar field, d mu psi star, with a mass and quartic coupling. So if you remember what we did yesterday, we took this Lagrangian and we went ahead and did the decomposition into amplitude and phase. And then once we got the superfluid effective theory, we then went on to take the non-relativistic limit. So the alternative approach I want to discuss briefly is to take the non-relativistic limit from the get-go. And you will see why this is sort of useful. And the way to take this non-relativistic limit is to do a field redefinition of this complex scalar psi, and I'll define a new variable related as follows. So 1 over root 2m, and I will denote the new field variables as capital psi of x and t. And crucially, these two differ by e to the minus imt. So if you think about this evolution of the phase as e to the I energy times time, this is just saying that we're sort of already taking into account the rest mass energy of those particles. So making that substitution into the Lagrangian above, in particular, I'll leave that to you as an exercise, but in particular, if you take the time derivative term, you'll find various contributions here, 1 over 2m, and then of course you'll get a piece which involves quadratic and time derivative of capital psi. Then you'll get terms that are linear in time derivatives of capital psi, which comes about by differentiating the phase, like so. Psi star, and then of course, lastly is when the time derivatives only act on the phase, which gives you plus m squared norm psi squared. And this plus m squared norm psi squared, convince yourself, will precisely cancel the minus m squared term in the Lagrangian. And anyways, when you all feed it in, and really it's a nice exercise to do, you're left with the following non-relative. I forgot to say, of course, in this non-relativistic approximation now, of course, we assume that the time derivatives of psi are negligible compared to the mass. So in particular, this term over here, which involves psi dot, is negligible compared to the m psi dot term. So you drop it, okay? So what you're left with is the following Lagrangian, which involves one time derivative, spatial gradients remain. And of course, you have the interaction term, g over 8m squared, sine to the fourth, like so. Now, if you take this non-relativistic action and you vary with respect to psi star, you obtain the following Schrodinger-like equation, that I psi dot is equal to minus 1 over 2m Laplacian squared plus g over 4m squared norm, like so. Okay, so it's a nonlinear version of Schrodinger's equation for psi, and it's a famous equation known as the Gross-Pitayevsky equation. So I mentioned this for completeness. This is another well-known approach to study superfluidity. And now from this formulation, we make another change of variables, which will be familiar to you from quantum mechanics. Thinking of psi as a wave function, we know from quantum mechanics that it's useful to perform a Madelung decomposition. In which you express the wave function in terms of an amplitude and a phase, and the amplitude is immediately recognized, of course, as what sets the charge density. So this is square root of n, right? E to the I theta, theta being the phase, and n, which is the number density, I can write as the mass density divided by the mass of the dark matter particle. That's one thing, okay? So that's the usual decomposition. And what will happen momentarily is you see that I'm splitting the complex field, complex wave function, in terms of two real variables. So both rho here and theta, of course, depends on space and time. So you decompose it into terms of two real variables, and the above Schrodinger equation will of course itself decompose into two real equations, two first order real equations. And for this purpose, to cast the resulting equations in a familiar form, it's convenient to define a velocity field, v, as 1 over m times the gradient of that phase. In quantum mechanics, this v is, of course, closely related to the current, the spatial current for conservation of probability. In any event, it's a very nice exercise for you to do in the privacy of your room. What you obtain upon substituting, you obtain the following. So the Schrodinger equation above will give you an equation for the norm, which is just a good old continuity equation. And you'll get an equation for the velocity. V dot grad times V. And then on the right-hand side of this guy, you get two contributions minus the gradient of the pressure. And here, the pressure for the particular superfluid of interest, so the one with quartic interactions that we're discussing, as we showed yesterday, you can express the result in terms of the chemical potential or equivalently in terms of the density. When you do so, the pressure is G over 8 m to the 4th times rho squared for this particular superfluid, okay? And there's an additional term on the right-hand side. If you look at saccharide, for example, you'll see this as well. You'll find that this is n over 2m squared spatial Laplacian of the square root of n divided by the square root of n. And this last term is truly arising from quantum mechanics. Sometimes it's casually referred to as a quantum pressure. In particular, this term is the term that perhaps already Lamb has discussed this in his lecture. This is the term that plays a role in fuzzy dark matter to get a halo. Whereas in our case, the term that is most relevant is the gradient of the pressure, okay, coming from self-interactions of the superfluid. In any event, this equation up to this last term, owing to quantum effects, is recognized as Euler's equation. So somebody yesterday was asking in particular, how do I see superfluidity from the description we've just given? I gave yesterday a sort of microscopic answer for this in terms of Cherenkov, the analog of Cherenkov radiation. And here you see it in a sort of hydrodynamical language. you clearly see that these equations have no dissipation, no viscosity. So these equations are inviscid. That's number one. And number two, you also see that in this hydro understanding or interpretation, the velocity, as defined here, is potential flow. It's the gradient of a potential. So this is potential flow. And in particular, it instructs us that the flow is irrotational. Does that make sense? Any questions?
I have a question. I'm not exactly sure if it's related to what you just said, but maybe. So in Lamb's lecture that we just had, we were talking about some really similar concepts. For him, talking about fuzzy dark matter, the potential looked like a tilted Mexican hat potential. Could a tilted Mexican hat potential also give us this superfluid dark matter?
Yeah, right. So, so if I'm not mistaken, in the context of fuzzy dark matter, one is looking at an axion type potential, which is a cosine yes. Potential, right? Okay. Right. So for all intents and purposes, what happens in that context? So you have this cosine potential, like so, but ultimately, once these axions are produced, you're mainly describing the fluctuation, the oscillations around the minimum of that potential. Okay, sorry for the noise. And so from that point of view, in that particular context, one can show that the quartic interaction, so this field, because it's in a cosine potential, will have quartic interactions as well, but those are very weak. Okay, so effectively, fuzzy dark matter is a free real scalar, okay, with a mass, small mass. And even with a real scalar, in the non-relativistic limit, you can perform a similar description in terms of a complex wave function in the non-relativistic limit. And you would get down to basically, I don't know if he's shown it already. Unfortunately, it was too early for me to listen to his lecture, but you get to very similar equations, hydrodynamical equations, except that, of course, the pressure is negligible. So the short answer to your question is that, I mean, from the sort of the continuum of different phenomena, superfluidity is a version of fuzzy dark matter. They're both Bose-Einstein condensate, except that in the superfluid case, the interactions are important. And so if you want, as I'm going to show a bit later, the reason you get a core of superfluidity in our case is because of the pressure. It's the pressure that supports the gravitational force, whereas in fuzzy dark matter, it's really this quantum term, the last term, which expresses the uncertainty principle, if you want. That's what stabilizes the halo. Does that answer your question?
Yes, it does. Thank you.
Thanks so much.
And one more for you, Justin. So
yes.
for this inviscid that you say at the end here, so if I saw a term like rho v, would that tell me that it's not a superfluid? Is that type of term we're looking for here?
Yeah, it will be the term that appears in Navier-Stokes equation. The kind of, the moment you, the shear and bulk viscosity terms, which are absent here. Yeah.
Thank you.
Thanks. Okay. Okay. Let me make another brief point. So far we've been discussing, generally speaking, superfluidity and dark matter superfluidity in particular. The moment you say that dark matter could be a superfluid, naturally you ask what kind of superfluid could it be? And the idea that we have with Lasha Bergiani and myself was, if you recall this Lagrangian that I showed in the very first lecture of the Mond Lagrangian, the Bekenstein-Milgram action. So let me refresh our memories on this. So this Mond Lagrangian was of the form minus 2/3 and Planck squared over A naught grad phi squared square root of grad phi squared, and then this couples to density by rho Okay, I think in my slides, I had a 1 over m Planck in the last term. That was a typo. Okay, I think this is the correct action. This is the Bekenstein-Milgram action. And you'll recall that this A naught characteristic acceleration is 1/6 the speed of light times the Hubble constant, which in natural units is approximately 10 to the minus 33 electron volts. Okay. So as we discussed, when you think about, in this Mon interpretation, initially, this phi field is to be thought of as some fundamental field that mediates a scalar force on top of gravity. And in particular, in that case, you have to swallow or contend with the fact that the kinetic term, the gradient term for this field is highly unusual with this non-analytic power. But the idea that we had with Lasha is that in the context of superfluidity, as I've alluded to a number of times, it's natural to identify phi with phonons. In other words, to think of this theory as an effective theory of phonons in the dark matter superfluid. So in this context, right, the natural way we would write this down for the phi field would be as a P of X theory. So we would write it, and the way I'm writing it here is a bit conventional, but one way to think about it is as follows. And then this phi must couple to ordinary matter, rho sub B. So a couple of comments. So remember that X here is the non-relativistic X that we discussed yesterday. And it really is to be thought of as arising from the superfluid phase. And the other comment is, if you look at this last term, which couples pi to rho, you remember pi had a shift symmetry. That's how we justified the P of X. But this last interaction term, of course, breaks the shift symmetry explicitly. There are two ways one can think about this. One is from a particle physics point of view. It breaks the U1, but only at the 1 over m Planck level. So very weakly, and therefore it's a technically natural assumption to have such an operator. And in fact, such operators do arise in superfluidity in various ways. For example, I'm going to show you an example in a few moments. If you have two component superfluids, or if the baryons were to couple to the vortex sector, you can have operators that break the continuous U1 down to a discrete U1. Now, when you do the matching between these two Lagrangians, so the field redefinition that relates the two, to bring it to the Milgram-Bekenstein form, is to define phi to be lambda over m Planck I. Okay, so that's how you would just, for example, relate this term with this term. And when you do that, you will be able to read off what the characteristic scale A naught is in terms of the parameters of this Lagrangian for the superfluid. And you'll find that this scale A naught is related to the scale lambda that appears in the superfluid Lagrangian as the square root of A naught times m Planck. So this is the usual numerology, that the geometric mean of the Hubble parameter and the Planck scale is roughly a milli-electron volt. And this is sort of interesting because you see that all the scales in the superfluid Lagrangian, so remember the mass was the order of an electron volt. And now this interaction or coupling scale lambda is a little bit below the EV scale. Everything is around EV-ish. Okay, so that's kind of nice. And of course, as you all know, MeV, milli-EV is the scale of dark energy. So in principle, it suggests a potential possible connection to cosmology. So the basic picture then with this Lagrangian is that it is in fact dark matter phonons that mediate a long-range force above and beyond gravity, and that long-range force is, given the form of this Lagrangian, will be that geometric mean of A naught and the Newtonian baryonic acceleration. One quick comment is that unlike a usual scalar that would mediate an additional force, here crucially, this force only occurs in regions of superfluidity. So superfluidity is a prerequisite in order to have this new force. In particular, if there's no superfluid, parts of the universe, particular galaxy clusters, are mostly not superfluid, then no superfluid implies no MOND. So you see, just from a purely philosophical standpoint, you see somehow historically dark matter, particle dark matter, or modified gravity were viewed as two extremes, no, one or the other, or completely different entities. Of course, you could combine dark matter and an additional long-range force, but usually it would be done by adding a scalar, which mediates the force, which in principle has nothing to do with dark matter. Here, quite interestingly, right, this modified gravity, so to speak, is really emerging from the dark matter itself. Anyways, this got some philosophers of science very excited that there was this sort of, this kind of different hybrid possibility. But of course, from a physics point of view, it's completely understandable. Okay, let me pause here for questions.
Yeah, I have one.
Yeah.
So this is just kind of a very general question, but I'm having trouble understanding qualitatively how it would be possible to have a force that only exists when you have a superfluid.
Yeah, I mean, it's a, how should I say, if you want, a force requires coherence. You know, you need some mediator which is able to coherently communicate this force across long distances, right? If you're in an environment, and that coherence is precisely what the superfluid state offers. If instead you're in an environment where you're not superfluid, then really these dark matter particles are just acting individually. They will still have some short range, extremely short range effects, but they cannot sort of organize themselves to mediate a force over astrophysical distances. So that's the basic idea.
Okay, so the field exists everywhere, but the only important contributions of the force are in superfluid regions?
Exactly. So somehow in regions where there's no superfluidity, then it's just effectively like collisionless dark matter particles. And all you're getting is the gravity of that dark matter. But in regions where they do organize in a superfluid state, now there is the possibility of having these long range interactions owing to the coherence of this state.
Got it, thank you.
Yeah, thanks.
Okay, sorry, may I also ask a question? So now that you said that there are like regions where DM is superfluid and then they are not, so I mean, I'm guessing that there is like, let's say, smooth transition then between the regions, and what about then the forces and how do they flow into each other, or how would I say?
Yeah, that's a good question, right? So in particular, yeah, and the answer is I'm not, to be honest, to answer this would require probably simulations, but an interesting situation, I mean, I'll show you in a moment a few slides, but an interesting situation is, let's say around the Milky Way galaxy, for example. So there's a superfluid core. Superfluid core has to be at least as large as the extent of the disk, and even including the gas, if you see it. So 50, 60 kiloparsec or so. All right, so there's a superfluid core. And now the interesting question is, so if you have satellites, nearby satellites that are within this core, they will experience this additional force. But faraway satellites, let's say Draco, okay, that are further away, these in principle should not experience the force. And to be clear, in order to have the force mediated between two objects, of course, they both have to be within the superfluid bubble. So it's a really interesting question to ask what happens, but I think that's what perhaps you have in mind, that what happens, let's say, when a satellite will enter the superfluid bubble, and how this would change the dynamics. I think this would be a really fascinating problem. We just haven't had a chance to simulate it.
Thank you.
Yeah. So let me move on perhaps to, I also had a few slides to show. See? One moment. You see the slide?
Yes.
Great. Let me just make sure. Yes. Okay, perfect. Right. So just some few basic remarks. So related to, in fact, the question that was just asked. So if you let's say we want to actually describe the superfluid profile in a galaxy. So let's first ignore the baryonic contribution. Let's just think about dark matter self-interacting with itself. So if you assume hydrostatic equilibrium, it's a very nice exercise, and I'll put more details in the lecture notes. But as usual, you would equate the gradient of the pressure to the gravitational pull. You get an equation of this type, and if you substitute the equation of state for the particular superfluid of interest, where the pressure scales as density cubed, you find this sort of chord density profile shown here, where the density is smooth at the origin and then monotonically decreases till the size r. Yeah, the equation that you end up getting is a Lane-Emden equation. It's a famous equation in astrophysics in particular. And interestingly, the size of this core, when you work it out, has the following parametrics. Okay, so it depends, of course, on the mass of the core, m. It also depends on the mass of the dark matter particle and that coupling scale lambda. And this is kind of interesting because in this sort of sausage factory, what went in was the solar mass. Okay, so mass in units of solar, that's the mass galaxy. The mass of the dark matter particle, which is EV, lambda, which is milli-EV, and otherwise the Planck scale or Newton's constant. And when you put it all in the sausage factory, quite interestingly, what comes out is a core radius of order, 50 kiloparsec or so. So an astrophysically relevant scale. So that's kind of interesting. Now, of course, you could say, well, the dark matter halo in our galaxy doesn't sharply terminate like this. This is because the discussion here is at zero temperature. And as we've discussed at the beginning, of course, in realistic halo, like our galactic halo, dark matter particles are whizzing around. They have a velocity dispersion, and therefore this is really at finite temperature. So if you do more carefully, a little bit more carefully, the calculation at finite temperature, this is what I obtained with my student and a condensed matter colleague at Penn, Tom Lubensky. So this is roughly the picture of how the profile looks like. So there's a superfluid core. You see it here in the inset. Okay, there's a superfluid core. But then when the density drops sufficiently low, then your particles start to behave as dark matter particles, but still in thermal equilibrium. And as a result, the profile turns over to an isothermal profile with approximate 1 over r squared fall off. And lastly, when the density drops sufficiently, then even thermal equilibrium cannot be maintained. And then we weren't able to calculate this, to be honest, but the expectation is that you would eventually just match to an NFW sort of CDM style profile. You can fit rotation curves. So here to keep in mind that within the superfluid bubble, there are really three forces that are acting on a test baryonic particle. So one is the gravitational acceleration from the baryons themselves, gas and stars. There is the gravitational Newtonian force due to the dark matter, as usual. But then on top of it, there's the Mondian force coming from the phonons. And we were able to fit galactic rotation curves. Of course, this is not so surprising because, this is reproducing the Mon behavior, which, as we know, is quite successful at fitting rotation curves. Okay, this is fun. So as you probably know, Andromeda galaxy and the Milky Way galaxy are on a collision course. In about 5 billion years, approximately, they will merge together. Also, there's a triangulum galaxy, which comes along to make it a fun three-way dance. But you see that eventually they come together and they merge. And you see that the way they merge, if I just quickly replay the movie because it's fun, You see that the way they merge almost appears that there's some friction force because they're sloshing around and rapidly coming together. And this is a well-known effect in gravity. It's known as dynamical friction. Okay, the fact that these guys, and it's really what makes galaxy mergers efficient. It's this sloshing around due to dynamical friction. So what is dynamical friction? Dynamical friction is the following simple fact, that if I take a body moving through a gas of particles with only interactions being gravity between them, then as this massive body passes through, it attracts particles in the medium, okay, and thereby creates an overdense region in its wake, which therefore acts to pull it back. Okay, so it's simply this rearrangement of the medium particles, which results in the body effectively experiencing friction force, even though, of course, gravity is conservative fundamentally. Okay, so it's sort of an entropic force. Oh, by the way, this is how it's going to look in the sky 5 billion years from now. Okay, so you see, you start with the Milky Way, and then Andromeda is coming, and then poof, everything goes messy, and at the end, you're left with an elliptical galaxy. By the way, Avi Loeb at Harvard, who studied this phenomenon, has written papers on this future collision, has said that this will be one day his most cited paper in 5 billion years. So anyhow, but in the superfluid context, the story is a little bit different. I mean, not 100% different, but there will be some small differences, owing to the fact, as we have discussed, that the superfluids, at least themselves, do not experience dissipation if bodies moving through them, or they're moving relative to each other, at a relative speed less than the sound speed, so for subsonic motion. And this is Landau's criterion, and last time I gave a microscopic discussion for why that is. So if you were to do simulations, and we're still planning to do them, for galaxy mergers, then at least for the superfluid cores, one would expect suppressed dynamical friction if the infall velocity is less than the sound speed within the superfluid media. On the other hand, if the infall velocity is supersonic, then as you'd expect, this will excite particles out of the condensate through Landau's arguments. Particles will be excited out of the condensate. You will momentarily exit the superfluid phase, and you should have, therefore, dynamical friction as usual. You see, because dynamical friction really relies, as my picture showed, on the individual rearrangements of particles. And that's, of course, impossible in the superfluid, where the only excitations are sound waves. They're coherent excitations. Now, of course, I should say that ordinary stars and the outskirts of the dark matter halo, which are not in the superfluid phase, those will experience dynamical friction as usual. But at least the merger history in this model should be a little different, somewhat different, hopefully observationally different, owing to this slight suppression of dynamical friction. Okay, of course, maybe many of you are wondering how dark energy can fit into this picture. So I'll briefly mention this, and then my last point. So dark energy, we wrote a paper on this. There's a sort of very nice natural way that dark energy may arise in this context. And the basic idea is as follows. In the lab, people have studied mixtures of Bose-Einstein condensates or mixtures of superfluids, which can arise, let's say, if you have cold atoms and you have two states of these cold atoms, maybe ground state excited states, a mixture, these populations. And as a result, and both populations can be in superfluid state. So you really have this mixture of two superfluids, okay? And as we know from superconductivity, there's a completely analogous phenomenon in superfluidity. They can interact, these two components, and they interact with Josephson-style coupling as follows. And what this does is it breaks the continuous U1 symmetry down to there are initially two U1 continuous symmetries for each of the two fields, and it breaks it down to a diagonal subgroup in such a way that what you get are these periodic cosine potentials. So the basic idea we had is that the energy difference between the two states will lead to a potential, which is the cosine squared of that energy difference times time, and that kind of time-dependent potential, which simply owes to the interaction energy of these two forms of dark matter can back react and drive late time acceleration. Okay, let me maybe conclude my set of lectures. So I think in summary, there is no question in my mind that cold dark matter works exquisitely well on the largest scales in the universe. In galaxy clusters as well, it does pretty well. But I think from my point of view, the tight scatter of these empirical scaling relations in galaxies remains puzzling from a CDM point of view. It's an open question whether CDM can fully explain them. It's an interesting question to resolve. But aside from this motivation, one can consider dark matter superfluidity in its own right as an interesting form of dark matter. But anyways, this was my motivation. And from my point of view, these tight relations may be suggesting that there are new long-range interactions taking place on galactic scales. And in this dark matter superfluid context that we've developed, it's kind of interesting because both dark matter and muon are not, mutually exclusive. Rather, they are different manifestations of the same underlying physics, namely dark matter superfluidity. And as we discussed, there's some potentially rich implications for mergers of galaxies. Oops. Can you still hear me?
Yes, there
Okay.
was some disturbance from that.
Okay. Yeah, and lastly, an interesting question is, so if you remember in yesterday's lecture, I mentioned the unitary Fermi gas, which is a gas of cold atoms that has been well studied in the laboratory, which has also these non-analytic powers as a superfluid effective theory. So to me, this is sort of an interesting possibility, whether we could actually find a cold atom system that would have the desired equation of state for this muon effective theory. And in particular, whether using that, one could study the analog of a galaxy, let's say in a cold atom system. So I'll leave it here, and of course, I'm happy to discuss more with questions.
Is there any question? Yes, if you want here.
Hi. So as I understand, in the context of the dark matter superfluid, we recover cold dark matter on cosmological scales. How does that work? It's just because the density is so, the fluid is so dilute that these interactions are not important. How does this work, recovering the cold dark matter limit?
Yeah, pretty much that's correct. At low enough density, you recover. You can recover basically collisionless dark matter. That is correct. That's why if you want the NFW profile is recovered.
Can we see that from the Lagrangian you wrote? Or?
Well, not per se, because the Lagrangian I wrote, how should I say? Yeah, in some sense, yes, because you see that if you remember the dispersion relation that I wrote down yesterday, okay, in fact, right, which had a linear term, CSK, and then there was a quadratic correction, k squared over 2m. You see that if you go at low enough, let's see, so how does this go? Yeah, so somehow if you go to regions, once the density gets low enough, then the condition for Bose-Einstein condensation simply breaks down, right? So remember, Bose-Einstein condensation requires densities such that that the Brody wavelength is longer than the average particle separation. So as the gas becomes sufficiently dilute, then this condition breaks down, and there's no Bose-Einstein phenomenon anymore. So really, in that limit, you just behave like collisionless particles.
Okay, makes sense. Thanks a lot.
Thanks so much.
I have a question about the density profiles that you're talking about in galaxies.
I'm so sorry. Can you say again?
Yeah, I have a question about the density profiles of galaxies.
Yes.
So you said that you were not able to do the calculation outside of the isothermal region.
Yeah,
why is that?
right.
Is there some problem you ran into, or?
No, it's just the description itself. So somehow it's sort of related to what I just mentioned, that you start out from this effective. I mean, in principle, we could do it, but it's just the way we solve things, right? So you take your theory, which is, let's say, the quartic complex scalar as a simplest example. And as we've shown explicitly there, you can, of course, nicely describe this in a sort of by expanding around the condensate and having your fluctuations being the phonons, etc. But that presumes that there's a Bose-Einstein condensate, right? So if you want, once you go to the outskirts where the density is so low that there's no Bose-Einstein condensation, I mean, the theory that you wrote down, the Lagrangian, is still valid. It just now describes a collection of particles. And it's just tricky to find the approximation scheme that continuously goes from one to the other. So I can say one quick thing about this. So I mean, these are questions that are studied in the statistical mechanics community. So let me just collect my thoughts. So the way we approached the description of Bose-Einstein condensate, you'll remember we applied this mean field approximation, no, where we said the condensate, we write it down as if it's completely not influenced by quantum fluctuations. But in reality, quantum fluctuations do back react at some level, okay? And one can treat those quantum corrections, there are various approximation scheme, you know, Hartree-Fock, Bogoliubov approximations, etc., which takes them into account. The problem is that those are precisely terms that these corrections becomes quite relevant once you approach these outskirts of the galaxy. So the short answer to your question is being able to find a self-consistent scheme where these quantum fluctuations back react onto the condensate is tricky to be able to completely track the phase transition, etc. So it's not unfeasible, it's just challenging.
Sounds like it. Thanks.
Yep, thank you.
Hi, Justin. Thank you for the nice talks. I have 1 to 2 questions. So the first thing I'm wondering, I mean, we start with these phi or psi fields, and we calculate all this superfluidity. But I mean, it really doesn't answer the question of what this field is, right? So I guess I'm kind of wondering, is there any kind of laboratory tests or something like this that people propose to figure out more about this thing?
Oh yeah, that's a wonderful question, right? So, right, so there are two sides to this. So, I mean, the psi field, you know, could be it could be that it's just some scalar field, just, you know, analogous to what people think about with fuzzy dark matter. And, you know, if it is that kind of scalar field, you know, the shift symmetry that it has, in principle, it could have axion style interactions with ordinary matter. So coupling to E and M in the E dot B type interactions that one sees. That's one possibility. Of course, with a mass of order electron volt, that makes it very difficult to probe with axion detection experiments. More interesting, though, the more interesting answer, perhaps, to your question is in the root of cold atoms. Okay, so, you know, I think the dream for me would be to actually find a cold atom system that has that equation of state, and I think that's where it points. That's where the physics is pointing, in my opinion. That the fact that it has a similar equation of state as unitary Fermi gas, which is a gas of fermionic atoms, suggests that this may be the actual description of dark matter. Okay. Anyways, these are speculations, obviously, hallucinations at best, but that would be kind of the idea. So the UV completion, in some sense, is not really standard from a particle physics point of view. It's, yeah. Sorry. Go ahead.
Can you tell me more what you're thinking about with these cold atoms? I don't know exactly what you mean. Do you mean like standard model cold atoms or something dark?
Yeah, no, I would mean the dark matter analog of cold atoms. So what people have found with this unitary Fermi gas is they take some fermionic atoms, some fermions rather, and then they can tune the scattering length by varying external magnetic field. And by tuning this scattering length, they can probe continuously the range where these fermions behave as a BCS superconductor or BEC, where they form basically tightly bound bosonic atoms. And in between, there's a resonance phase transition known as the unitary Fermi gas. And that's a super interesting phase. And in particular there, the equation of state of that superfluid also has these half integer powers. So that's what, in some sense, piques my interest, that, yeah, this, it's not a very complete answer, but that's kind of it will be a sort of dark matter analog of, cold atoms in the lab.
Okay, I think I understand. So, I mean, this is really, I mean, the story with these cold atoms, we're just saying we have pairs of fermions forming these in these bosonic states, right? Or is this something different?
No, that's exactly right. So with the fermion, what happens with these fermions is, if you're these fermionic atoms, is if you can be in one regime where they form weakly bound states, which are forming basically Cooper pairs. And that's why they describe superconductivity. And at the other end of the spectrum, they're more tightly bound states, which are therefore behaving as basically elementary bosons, and they form a BEC. And in between, there's this transition.
Sure.
So it will be some kind of state of dark matter that, that would behave in this way. But I don't have anything more precise to say about this.
No, that's clear. Thank you. And now for the second question. So this is my first time seeing something like modified gravity. And I don't know, it still felt a lot like particle physics, I guess. So I'm wondering if you can give me I don't know, what else do people try for this modified Newtonian dynamics? Does it always start?
Oh, yeah, there's all kinds of ideas out there. I mean, well, how should I say? There were proposals. I mean, some people just tried to, keep going and try to write down a relativistic theory without dark matter. So Bekenstein did that in 20 years ago or so, in which ultimately you need not just a scalar, but you need a vector as well. It has this really complicated action, which kind of tells me that that's it's not meant to be made relativistic in this way. And then there are other proposals. So Eric Berlinde in the last few years has come up with some other way to get this kind of behavior, but not from particle physics, but from string theory type argument, which I don't understand, to be honest. But yeah, so there's a range of proposal out there. I'm biased, but I think the dark matter superfluidity is in some sense the most conservative, no? Because in superfluidity we've observed, okay, phonons we've observed. Dark matter being a superfluid is not entirely crazy. So I think in the spectrum of this modified gravity, I think it's well, I don't want to say reasonable, but yeah, somewhat reasonable.
No, yeah, I guess it makes sense, and it is satisfying. I guess if from a naive standpoint, it doesn't even seem like it's modified gravity. It just seems like it's the implications of particle physics, no?
Yeah, I mean, I would say modified gravity is at the basic level is just new long range force, no? So, and here's a way to introduce a long range force without really modifying fundamentally what is gravity. The rest of the gravitational sector is untouched.
I see. Very good.
Yeah.
Thank you.
Thanks so much. Yeah.
There's one question on Zoom on the chat.
Sorry. Yes. Let me quickly look at it. Sorry, I can't somehow it. Yeah, there we go. Okay. Oh, that's a nice question. Right. So question is.
People here after. So the question
Yes,
is,
I will read it. I will. Okay, go ahead.
The predictions for a galaxy collision, I guess cluster collisions with superfluid dark matter are consistent with the observed galaxy cluster collisions, such as the bullet cluster.
Yes, great question. So I didn't have a chance to discuss the self interactions of this superfluid, but as I briefly alluded to in the first lecture, to maintain coherence of the superfluid state in the galaxies, these particles have to be, of course, self-interacting, and they have to be self-interacting sufficiently strongly. So specifically, what you find is that the interaction cross-section, here I can just really quickly write it for completeness. Okay. Yeah, what you find from requiring that you maintain thermal equilibrium, I'll just write down the punchline, that the cross-section per unit mass has to be greater than m over e to the fourth centimeter squared per grams. Now, bullet cluster, as probably Annika discussed, for self-interacting dark matter for SIDM, the constraint on sigma over m is roughly that it's a centimeter squared, less than centimeter squared per grams. Now, more precisely, I think in their simulations, they found some 0.1 or 0.5 numerical factors, but yeah, roughly it's centimeter squared per grams. So this tells you that if in order to have a window that is compatible between these two statements, the mass of the dark matter particle has to be somewhat below EV, but it's raised to the fourth power, so that helps substantially. So just to say, although to be fair, this analysis of the bullet cluster and similar merging clusters, by now there's like nearly 100 of such clusters. To be fair, of course, they're done in this SIDM framework, but in general, really what they constrain is the amount of energy that's dissipated in the merger process. And so just applying that logic, yeah, you would find that if the mass is somewhat below EV, then there's a window where you can satisfy the bullet cluster. Yeah, that's a very nice question. Thank you.
Hi, I have another question. If I recall correctly, in one feature of superfluidity is the formation of vortices.
Ah, yes, correct. Absolutely, yeah.
I mean, if it happens that these have some consequences on
that's a wonderful question. So we've looked into this. So as you know, as you correctly point out, if you take a superfluid and you rotate it sufficiently fast, there's a critical angular velocity. And above the critical velocity, the superfluid doesn't carry the angular momentum homogeneously, uniformly. Rather, it breaks up into vortices, into an array of vortices. And and we showed analytically, indeed, that a rotating galaxy will indeed is rotating sufficiently fast to form this array of vortices. Unfortunately, the healing length, so the size of the core of these vortices, is set basically by the Compton wavelength. So it's of order m inverse, which is tiny. So in our case, these vortices are microscopically small, and in fact, they have very small tension. So at least I don't think they would have a direct impact in our case. By the way, in fuzzy dark matter, as I'm sure Lam will discuss, because their mass is so much smaller, 10 to the minus 22 electron volts, their vortices are far more prominent astrophysically. But in our case, they're tiny. Now, that being said, as I briefly alluded to, this kind of coupling between pi and rho b, that can occur if rho b were to couple to the vortex sector of the superfluid. It would give rise to a sort of cosine theta type coupling. So anyways, it's a great question you're asking. At face value, back of the envelope, it doesn't seem that they would have strong observational implications in our case, but they could have for these kinds of couplings.
Okay, thank you.
Thanks so much.
Okay, thank you very much, Justin. I think we have to wrap up and finish
Yes.
here. Thank you again very much for the lectures and for the discussion.
But can I just say in 10 seconds, I want to thank you again, Khoury and Babette, for putting this together. It's really wonderful. And I want to thank everybody in the audience that, you made this very interactive, which is truly remarkable given all the obstacles and technological hurdles. So thanks so much for making this fun for me. Thank you.
Okay, so let's clap for everyone.